Hello, my name is Andy Schweitzer, and this is our final video on stoichiometry. And this topic is called percent yield. Now, anytime you're making something, there's a chance that how much you think you're going to make isn't actually what you get. Now, an example I might make is that if you have a garden, let's just say this is your plot of land, and you plop down 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's just say you put a 10th one right here. Okay, you plant 10 seeds, and you water them, and sunlight shines, and it gets warm, and all of a sudden things start to sprout. Okay, so this one sprouts, this one sprouts, this one nothing. Sprout, 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 nothing, nothing, and this last one sprouted. So of the seeds you planted and the ones that actually came up and produced a plant, you were originally supposed to have, or sort of theoretically, yours versus what you actually happened. Now technically you wouldn't be able to get more than 10 unless you had some divine intervention, but in this case we were supposed to get 10 seeds. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So 7 of them came up, 3 of them did not. So that means this relationship, 7 out of 10, is the actual relationship. But if we were to make that out of 100 times 100, we would get a 70%, we call percent yield. Okay? Now, they're saying that if you had planted 100 seeds in here, that you would, at that point, using this relationship of 7 to 10, we would get 70 plants coming up as opposed to 100. Again, a percent is just a mythical or theoretical out of 100 type scenario. Now, how does this work as far as chemistry is concerned? All right, let's say we're going to make ammonia, okay? And ammonia is NH3, and the Haber process allows us to take nitrogen gas plus hydrogen gas at high temperatures and produce ammonia, NH3. This is ammonia. Balancing wise, we'll need to have probably a 2 here. 2 3 is 6, and therefore this would be a 3 here. We're now balanced. Okay, and let's just say that the nitrogen gas in the environment, it takes the nitrogen right out of the air. So let's just say this is an excess. Okay, and let's just say we have 1,000 kilograms of hydrogen. How much am I supposed to be able to get here? So my plan here is I'm going to take my kilograms, flip them to grams, because this is a gram to gram ratio. Either way, I can't, I guess I could leave in kilograms, but in this case, flip to grams, and then I'm going to flip it to moles, and then this is moles of H2. Use my stoic ratio to flip it to moles of NH3, and then I'll flip it back to grams and then back to kilograms. That's my plan. And this is the part that actually requires a little bit of thought. The rest of it is just a matter of using proportions. So let's do the math. 1,000 kilograms, dot line, get rid of kilograms and go to grams. 1 kilogram is equal to 1,000 grams, which in this case, if it stopped here, would be 1,000,000. Get rid of the grams and go to moles. This is the molar mass, gram to mole, weight to particle ratio. For hydrogen, that is 2 grams. 2 grams to 1 mole. Then I'm going to use my stoic ratio, moles to moles. Moles of H2 to moles of NH3. 3:2 ratio. I'm using the coefficients here. And then if I stopped here, it would be the moles of ammonia that I'm supposed to get, theoretically, on paper at least. So then flip moles to grams. 1 mole is equivalent to, well, let's add it up. This is 14, 15, 17 grams per mole. That's added up off the periodic table. And 17, dot line, get rid of grams, go to kilograms, 1,000 to 1, and that just cancels out that last flip there. But either way, plug it into your calculator, and we're going to get 1,000 times 1,000 divided by 2 times 2 divided by 3 times 17 divided by 1,000. And they're saying I'm supposed to get 5,667, if I round it, kilograms of this stuff. Okay. Now, conservation mass, you want to make sure, does this number make sense? Okay. These are very light particles. These guys here weigh 28 grams per mole. So every time I grab some of these, and I have lots of them, I will need a hydrogen to go with it. So this guy ran out to 0, so I have at least 1,000 kilograms of hydrogen here, and I believe that number makes sense, seeing as I have some very heavy hydrogens along with it. It give me a total of 5,667 kilograms of product. All right, so this is on paper what I should be getting if I'm in an industrially. All right, let's say that in the actual plant, okay, industrial plant, we're doing this situation, and they have to, they say, okay, well, we did the experiment, but we only got 4,880 kilograms of ammonia. Okay. Now, in a plant, you would, if you're running a business, you're trying to sell this stuff, you need to get a certain percent yield, and different chemical reactions give different percent yields, whether you're making ammonia or whether you're making ibuprofen. And either way, you'd want to sell your product. Historically, your company might require that you get a certain percent yield. And if you don't perform that percent yield, things need to change, or you could legitimately maybe even lose your job. Okay, because that's profits not being able to be sold. So you're losing money. All right. So what is our percent yield of this thing? So percent yield is going to be, now this is a mathematical analysis tool that's going to tell us how good we did. Okay. Originally, okay, it's going to be what I'm supposed to get divided by what I actually got. All right, actual divided by supposed times 100 to give us this mythical 100%, 100 value. I'm going to plug in here what I actually got is 4,880 kilograms divided by 5,667 kilograms. Make sure your units are the same, times 100. Now, if I got in 5,667, I'd be 100% yield. But in this case, that's not what I got. 4,880 divided by 5,667, and I got an 86.1% yield. And that is it. Pretty common for stoichiometry as far as how to analyze what you have versus what you actually got. Thank you very much.